Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so we are on question 2, organic chemistry, the nomenclature of organic compounds. And then we are given this statement here: study the table below and answer the questions that follow. So with these questions here, I have given you the strategy as to say that whenever you are answering this question, guys, make sure that you identify the homologous series of each and every compound. So this makes it easier for you to answer the questions here. So the first thing, before you even look at the questions, just try to identify the homologous series of each and every compound that you see in here. So now we can see that with the single bonds between the carbon atoms, that means that compound A here belongs where? In the alkane homologous series. And then looking at B, we can see that this is a hydroxyl group OH. This tells us that our B here belongs in the alcohol homologous series. Then we have C, it says C4H8O, which tells us that according to this molecular formula here, we can see that this corresponds to the general formula CnH2nO, which we know that this general formula is only applicable to aldehydes or ketones. So now, because there is nothing that specifies that this is an aldehyde or ketone, we will just say this should be an aldehyde or a ketone, right? So between the two. And then D here, we can say that this is still a hydrocarbon, but then looking at what we have here, we can see that we can form a double bond out of this if we can just try to break it down. So this is C, and then bonded to an H, and then another C bonded to 2 hydrogen atoms. But then looking at this, we can see that our number of bonds here are not complete, because remember, the number of bonds around the carbon atom should always be 4, right? So how do we make these 4 bonds around the carbon atom? We can make it by introducing another bond here to make it a double bond between the carbon atoms. Now, if we have double bonds between carbon atoms, we know that this is a functional group of the alkene. So our homologous series is alkene, right? So now coming to E, with E, because we don't have the value for X, Y, and Z, that means we cannot identify the homologous series as yet. So we'll just leave it like that. Hopefully, as we go along with the question, we will be able to identify where it belongs. Now, let's start with 2.1. It says, define the term unsaturated hydrocarbon. What is that? Unsaturated hydrocarbon? It simply means that this is a hydrocarbon. It's a hydrocarbon that has multiple bonds, right? Multiple bonds between its carbon atoms. Right? So remember, what is a hydrocarbon? A hydrocarbon is simply a compound that has hydrogen and carbon atoms only. So an unsaturated hydrocarbon has to be a hydrocarbon that has multiple bonds. Remember, multiple bonds means that it has either double bonds or triple bonds, which is either an alkene or an alkyne. Now, 2.2.1 says a letter that represents an unsaturated hydrocarbon. Because we have already identified that unsaturated hydrocarbons are either alkene or alkynes, looking at our diagram now, or our table, we can see that the only unsaturated hydrocarbon that we have here is D, right, which is an alkene. So for 2.2.1, our solution is D. Then 2.2.2 says IUPAC name of compound A, right? Now, be careful with this. Remember, whenever we are facing this question, the most important thing is to identify the longest chain, right? So you can start by looking at the straight chain first, and then we have 1, 2, 3, 4, 5. Right. Now let's confirm the other one. It's 1, 2, 3, 4, 5. Now at this point, you might think that pentane is the longest chain, but up until you see that this here, this zigzag shape here is actually the longest chain. So be mindful of that. The zigzag shape can also form the longest chain, right? So looking at this, all of that can be your longest chain. All of that can be your longest chain. Now you can ask yourself, why does it not stop here? It's because you cannot have your branch here at the first carbon or the last carbon, right? So now this is 1. When we start numbering, obviously we need to start numbering from the side where we have the closest disturbance, or where we have the closest substituent. Now numbering from this side, we can see this is 1, 2, 3. We only have a disturbance at the third carbon. But numbering from this side here, it's 1, 2, and then we can see that we have a methyl branch here on the second carbon. So the one that is the closest disturbance, it's from below here. So that means we can now say this is so this is our longest chain. Let's make it visible. Or this is our longest chain. And then numbering, this is 1, 2, 3, 4, 5, and 6. Right. So that means we have a methyl branch in carbon number 2, and then we have another methyl branch in carbon number 4. So note that always the branch is with the carbon that is not part of the longest chain. So as you can see, these carbons here are not part of the longest chain. Therefore, there are disturbances. There are methyl branches, right? So that means naming this, we will have to indicate the positions of the methyl branches. So that's 2.2.2. This will become 2, and then dash 2 comma 4. So it's 2 semicolon 4, and then hyphen di. Remember, it's di because we have 2 methyl branches. So 2, 4 di methyl, and then what's our longest chain? That's 6. So it's supposed to be what? Hexane. And that's how we name this: 2 semicolon 4 hyphen dimethyl hexane. Right. And then coming to 2.2.3 says IUPAC name of the positional isomer of compound B. Remember, positional isomer. What is a positional isomer? We say these are compounds with the same molecular formula but different positions of the functional group. Now we have compound B here, which we can see that the name in here will be what? It will be propan 1-ol. This is the name of compound B. But then now we are looking for the IUPAC name of the positional isomer. How do we make a positional isomer out of propan 1-ol? We only need to shift the position of the functional group. We shifted the position of the hydroxyl group. We take it from position number 1 and put it in position number 2. Now the IUPAC name of the positional isomer will be propan -2- ol. Propan 2-ol, right? And that for 2 marks. And then 2.2.4 says the IUPAC name of compound D. The IUPAC name of compound D. Now, obviously, to come about with the name of compound D, you obviously have to first understand how this would be drawn, right? So you first break down all this. So the strategy would be to first draw the structural formula. This is CHH. The first carbon is bonded to 3 hydrogen atoms. And then look at this. What is the meaning of this here? This means that you should expand this 4 times. So we have CH2 and then 4 here. This only means that you should expand that 4 times. So we have C bonded to H the first time, C bonded to 2H C bonded to 2 hydrogen atoms, third, and then C bonded to 2 hydrogen atoms, fourth. So that's 1, 2, 3, 4. We expanded it 4 times. And then followed by what? C bonded to an H. And then we have already discussed that in between is a double bond. And then we have C bonded to 2 hydrogen atoms. So now we can see our alkene compound. And then what's the name thereof? Remember, we are looking for the IUPAC name. So counting from here, that's 1, 2, 3, 4, 5, 6, and then 7. Right. So this will become what? Hept. Remember, 7 is hept. So that's hept -1 and then in. Right. Hept -1 in. So that's the name hept 1 in. Okay, then to answer 2.2.5, it says write down the balanced equation using molecular formulae for the complete combustion of compound A. Now, one thing that we know about a combustion is that it always has the general formula alkane reacting with oxygen to produce carbon dioxide and H2O. So that's a combustion reaction. And then what are we supposed to do now? We obviously should take our alkane, which we have identified that it is A, remember, of compound A. So they're saying of compound A because A is the alkane here. Now, what is the molecular formula of the alkane? We have to count how many carbons are here in total. 1, 2, 3, 4, 5, 6, 7, 8. Now, using the general formula CN, H2N plus 2, the general formula of the alkanes, let's find the molecular formula. We have C8, and then how many hydrogens should we have? That's 2 times 8 is 16, then plus 2, that's 18. So even if you were to count the number of hydrogens here, you'd find that there are 18. Then that's H18. Let's count. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that proves that. And then this will have to react with O2 to produce CO2 and H2O. Right. Now, at this point, we should balance using the method CHOR, the CHOR method. So we want to say CHOR on the left-hand side and then CHOR on the right-hand side. Now, this is how we use the method. We say how many carbons are on the left-hand side. As we can see here, there are 8 carbon atoms. But how many carbons are on the right-hand side? It's only 1. What integer can we multiply to 1 so that it gives us 8? That's 8. So we're just going to go ahead and just before the carbon there, we put 8. So now we have 8 times 1, that's 8 carbons. Now let's go to the hydrogens. How many hydrogens do we have on the left-hand side? That's 18. But on the right-hand side, we only have 2. What integer value can I multiply to 2 so that I get 18? That's 9, right? So just in front of the hydrogen or before hydrogen, we will put 9. So that's 9 times 2, 18 now. Let's go to the oxygen atoms. How many oxygen atoms on the left-hand side? It's 2. But how many oxygen atoms on the right-hand side? Now, careful. This is how we do it. That's 8 times 2, giving us 16. But 9 times 1, that's just 9. So 16 plus 9 gives us 25. So we have 25 oxygen atoms. But what integer value can we multiply to 2 so that it gives us 25? 25 is an odd number. That means there is no integer value that we can multiply to 2 so that it gives us 25. So how are we supposed to do this? We should take the 25 and then divide it by 2. So this gives us 25 over 2, of course. And then what are we going to do with the 25 over 2? We put it on the side where we have a shortage of the oxygens. So this is where we have a shortage of oxygens. So we want to have the 25/2. Simply take the bigger number, divide it by the smaller number when it gives you a fraction, put it on the side where we have a shortage. Now, remember, we should get rid of this 2 here. But how are we going to do it? We can multiply both sides by what? By 2. Now, the one thing that you have to note is that multiplying by 2 does not affect these numbers, the subscript. It can only affect the coefficients, right? So what I do on the left-hand side, I also do on the right-hand side. Now, if I multiply by 2 here, this will end up giving me 2. And then I still have the C8H18. Multiplying 2 by 25/2, I will only remain with the 25. So now I have the 25, and then still I have the O2. And then now, saying 2 multiplied by 8, that will give us what? 16. So I have my 16 here, but then still I have the CO2. Then if you say 2 multiplied by 9, that's 18, but then I still have my H2O. So note that the superscripts or the compounds themselves were not affected by you multiplying by this 2. Now let's confirm if this balanced out our equation. Let's now confirm again with the Cho method if our equation is now balanced. So, okay, on the left-hand side, how many carbons do we now have? That's 2 multiplied by 8, so that's 16. And then on the right-hand side, that's 16 multiplied by 1, it's 16. How many hydrogen atoms do we have? That's 2 multiplied by 18. It should be 36. So that's 36. And then again here, 18 multiplied by 2, that's 36. Right. And then let's confirm with the oxygens. That's 25 multiplied by 2 should be 50. But then again here, if we say 16 multiplied by 2, that's 32. But then 18 multiplied by 1, that's 18. If we say 32 plus 18, we get 50. So the oxygen atoms are 50. Now this is balanced. That means the left-hand side is equal to the right-hand side. And our equation is balanced. So that's how you go about balancing the equation using the Cho method. So please repeat it over and over again until you understand. Okay, now let's proceed. We have 2.3. It says the formula C4H8O represents 2 compounds that are functional isomers of each other, right? So this, remember, we said when analyzing, we said this can either be aldehyde or what? Or ketone, right? And then 2.3.1 says define the term functional isomer. What is a functional isomer? So to define functional isomer, we say these are what? These are compounds or organic compounds, compounds that have the same molecular formula, meant to say the same molecular formula, but different functional groups. It is also important to note that functional isomers belong in different homologous series. So that's where we used a cake, right, to say that the carboxylic acid is a functional isomer to an ester, and the aldehyde is a functional isomer to a ketone. So here we are given an aldehyde and ketone. Now, that's the definition of the functional isomer for 2.3.1. And then 2.3.2 says, write down the structural formulae of each of these 2 functional isomers. So given this molecular formula here, the same molecular formula, how do we then draw the structural formulas of each of this? Let's start with the aldehyde. Now, it's very simple to draw an aldehyde because we know the functional group, the formal group, would always be on the first carbon. So we just go, how many carbons? 1, 2, 3, 4. And then here we have our double bond oxygen, and then that's H. That's the formal group. Then that's how we'd indicate the aldehyde, as simple as that. So this is the structural formulae of the aldehyde. But what about the structural formulae of the ketone now? Now, the structural formulae of the ketone, still using the same molecular formula, it will be HC. And then now to make it a ketone, remember, the double bond oxygen should be in between the carbon that is surrounded by 2 other carbons. So let me erase this H here. It's not supposed to be there. Remember, we should have 4 bonds. 1, 2, 3, 4. And then this is H, and then C, H, H, and then H, right? So this here becomes the ketone. So because now we have shifted the double bond oxygen to a carbon that is in between other carbon atoms, this now changes to a carbonyl group. The functional group is now carbonyl. So remember, functional group here is carbonyl, but then the functional group here is formyl, right? So formyl group, and then this one is carbonyl group. So same molecular formula, but different functional groups, and they also belong in different homologous series, right? Then 2.4, we can see a throwback there. A 2 gram sample of compound E contains 1.09 gram carbon and 0.18 gram hydrogen. The molecular mass of compound E is 88 grams per mole. Determine the molecular formula of compound E by means of a calculation. So you still remember the one on calculating the molecular formula, which was the empirical formula first, and then molecular formula. So this is a throwback from grade 11. So make sure that you revise that. Okay, so now we are given a 2 gram sample of compound E. Compound E, we can see that it is made out of 3 elements: carbon, hydrogen, and oxygen. But then reading here, we are only told of 2 elements, 1.09 gram carbon and 0.18 gram hydrogen. So that means they were quiet on the oxygen. But then you do not have to be quiet as well. You need to calculate that. Remember, the 2 gram must be formed out of the elements carbon, hydrogen, and oxygen. Now, if you have carbon is 1.09 gram, and then you have hydrogen is 0.18 gram. You can see that adding the 2 does not amount to the 2 gram. So that means you must ask yourself, what is the value of the oxygen? So to find that, we need to say the oxygen, the mass of the oxygen is 2 gram minus 1.09 gram minus 0.18 gram, right? So it will make up the 2 gram. Then 2 minus 1.09 minus 0.18. This will give us a value of 0.73 gram. So that's our oxygen, 0.73 gram. Now, at this point, we know, having to apply our empirical formula, step number 1 is always to calculate the mass, the number of moles, to calculate the number of moles of each element, right? So it's always to calculate the number of moles of each element. So we have the carbon. To calculate the number of moles of carbon, we need to say M over the big M, which is 1.09 over the molar mass of carbon is 12. And then let's do it for the hydrogen. Number of moles of hydrogen, again, mass times the molar mass, that's 0.18 divided by 1. And then if we have to do it for the oxygen, again, mass times molar mass, then we have 0.73 over the molar mass of oxygen is 16. Now we want to find the values of each of this. 1.09 divided by 12 should give us 0.0908, right? So make sure that you always round off to at least 4 decimal places because you don't want to end up rounding off too much of your answers. Then we have a 0.73 divided by 16, and then rounding off to at least 4 decimal places is 0.0456 mole. Now we know the next step to this is to divide by the smallest number of moles, right? Now looking at all these numbers, we can tell that the smallest number of moles is obviously this one here. So we have 0.0908 divided by 0.0456, and then also here 0.18 divided by 0.0456, and then 0.0456 divided by 0.0456, right? Then let's punch this into our calculator. We have 0.0908 divided by 0.0456, right? So this is giving us a value of 1.99, which rounding off to the nearest whole number, this is just 2, because 1.99 eventually goes to rounds off to 2. Then 0.18 divided by 0.0456, let's see that it gives us a value of 3.94 something, so which rounds off to 4. And then this one here should obviously round off to 1, right? Then now to find our empirical formula, remember the ratios that we have here are the simplest whole number ratios. So that means this will be C2H4 and then O, right? So this is the simplest. Remember this, we haven't found the molecular formula. What we have here is the empirical formula, the simplest whole number ratio of all the elements in the compound. So now that we have the C2H4O, how should we then calculate the molecular formula, right? So now I need you to save this. We have C2H4O, and then let's proceed. Allow me to just erase here. Now remember our empirical formula is C2H4 and then O. But then we are given that the molar mass of compound E is 88 grams per mole. Now to find the molecular formula, we need to calculate the molar mass of the empirical formula, C2H4O. Now this will be 2 multiplied by 12, because we have two carbon atoms, and then each carbon atom is 12 grams per mole. And then we have 4 multiplied by 1 plus 60. Now adding all that together gives us 44 grams per mole. So to find our molecular formula, we need to take the 88 grams that we are given. So it's 88 divided by the molar mass of the empirical formula, which will give us 2. Now this 2 here is supposed to be the 2 that we multiply with here to find the molecular formula. So to find the molecular formula, we take the 2 here, and then we start to multiply here. So that's C4 now. So that's 2 multiplied by 2, and then 4 multiplied by 2, that's H8, and then 2 multiplied by 1, that's O2. So this becomes our molecular formula. And then you can even confirm this. This should give you a molar mass of 88 grams per mole. And then that's it for calculating the molecular mass. It's just a question from grade 11 that they put in grade 12 just to see that you still remember that. So do not put it into a cold storage. Always make sure that you revise also the work from grade 11, because as you can see with this question, it does pop up. So, okay, that's it for the lesson, guys. Please press the thumbs up button if you've enjoyed the lesson and then you have also found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.